So now let's see how we can do calculations involving buffer solutions. So in the previous video, we gave a generic HA expression, or a generic weak acid expression. We say the Ka is equal to the H plus times the A minus divided by the concentration of HA. So if we rearrange this, we can say the H plus concentration is going to equal the Ka times the concentration of HA divided by the concentration of A minus. So if we wanted to figure out what the pH here is, we could take the negative log of both sides. So the negative log of the H plus expression is going to equal the negative log of the Ka times the concentration of HA divided by the concentration of A minus. We can use some logarithmic algebra here to rearrange this particular expression. So this is going to be the negative log of the H plus is going to equal the negative log of the Ka minus the log of the HA divided by A minus. Okay? In each of these particular cases, if we have a negative log of something, we can use a pH to describe that. So that's going to equal the pKa, and then we can kind of rewrite this expression. A lot of times you see equations in textbooks, you typically don't see them written with negatives, so we're going to say this is going to be plus the log of A minus divided by HA. And remember, if we flip these two inside the log expression, we need to switch the sign. And that's exactly what we did here. And this equation right here is a very famous equation involving buffer solutions called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation allows us to calculate pH changes involving buffer solutions. And in these buffer solutions and in this equation, this can be represented as the concentration of the base divided by the concentration of the acid. So we can also use this involving weak base expressions, and we sometimes won't have an A minus over HA in that case. But you typically see this written this way, and the pH is going to equal the pKa plus the log of the concentration of the base divided by the concentration of the acid. So buffers will work only in a certain pH range, and we need to define something called a buffer capacity, which will kind of give us an indication of which pH ranges our buffer will work. And the buffer capacity is the amount of acid or base a buffer can neutralize before a large pH change occurs. So buffers don't work over every pH range, but they do work over certain ranges. And the optimal pH occurs when the concentration of A minus is going to equal the concentration of HA. And in this particular case, the pH is going to equal the pKa. Because if we look back at this Henderson-Hasselbalch equation, when A minus equals HA, that we're going to have the log of 1, which will tell us that the pH is equal to the pKa. And buffers function best when the pH is equal to the pKa plus or minus 1. Okay, so in terms of the optimal range and the pH range at which buffers can function, typically they operate well and they function very well when the pH is equal to the pKa plus or minus 1. So when we design particular buffer solutions, we need to pick a particular acid or base that has a pKa right around the pH at which we're trying to operate under. So if we're operating at a pH of 7, we want to pick a Ka of around 1 times 10 to the minus 7, or a pKa of 7. Okay, we don't want to pick something that has a Ka of 10 to the minus 2, because that would be outside our buffer range. So this kind of gives you a glimpse of how we would calculate the pH in particular buffer solutions, and then what range these buffers would function best.